What we're going to do today, we're going to talk about simplifying irrational numbers. Remember, irrational numbers are numbers that, when expressed as a decimal, they go on forever and ever and ever without repeating. Um, the cool thing is, whenever you take the square root of a number, whenever you take the square root of a number, if unless you know that number happens to be a perfect square, you're very likely going to be dealing with an irrational number in that case. So, what we're going to do is we're going to look at a few realities here. The square root of 100 times 21. Now, this is happening inside the square root. But you may remember a little rule that said if I'm multiplying inside of a square root, I can split that off into multiplying two separate square roots. It goes the other way as well. Equality is two-sided, but I'll rewrite it just to be extra safe. You can combine two things into a single square root as well. You can go either direction. And there's going to be certain contexts where doing it this first way is going to be best. There's going to be other contexts where doing it this way is going to be best. So let's look at what we have with this one. Looks like we want to use this first rule here. The square root of 100 times 21. The problem is straight up telling us to split it up into two square roots. Like that. You'll notice, well, I guess, how much do they want us to do? Nothing just yet. Okay. You'll notice that we do that because this 100 is a perfect square, which means it'll have an easy square root of 10. And then you just have that square root left over, square root of 21, I should say. And the square root of 21, if you look at the prime factorization of 21, the only thing you can do is 3 times 7. Those are both prime numbers. You have no pairs of factors, meaning you only have a single 3 and a single 7. So square root of 21 is as simple as it can get. But the square root of 100 will become 10 because 10 times 10 is 100. So in simplifying this, we end up with that. And it is covered by that. So really this homework is just kind of follow along in some cases. Now, like I said, this one looks bad, but just look at closely what it's doing. Square root of 45 plus square root of 180. What it's going to do in the next step is it's going to take each individual square root and it's going to write it as a product, as two things being multiplied, where the first thing in each case is going to be a perfect square, and the second thing is just going to be what's left over. So square root of 45 is the square root of 9 times 5. Don't believe me? Well, let's look at 45. We know that's 9 times 5. We know then that 9 is 3 times 3. And so the square root of 45, there's a couple ways you can do it. They're doing it one way. The way we kind of talked about in class was to circle any pairs of factors, in this case the 3's, bring them outside of the square root with one representative. And then all you have left inside is what didn't have a pair. So the square root of 45 can be written as 3 square roots of 5. What they're doing, they're taking a little bit more circuitous route with this. And they're saying there's branching off the 9 and the 5, but it's just going to become 3 square roots of 5 down here. Square root of 180. Well, let's look at 180. Let's think, well, 10 and 18, that'll work. And then 10 can be written as 5 times 2. 18 can be written as 2 times 9. And then 9 is 3 times 3. So let's circle all of our pairs here. You have a pair of 2s and a pair of 3s. And you're going to take each pair out with only one representative. So the square root of 180 is, the pair of 2s will be represented just by a single 2, and it gets to come outside of the square root. The pair of 3s will be represented by a single 3, and we're multiplying. And then inside the square root still is the 5, which didn't have any pair. And then 2 times 3 is 6, so this becomes 6 square roots of 5. So this will become 3 square roots of 5 plus 6 square roots of 5. Now let's find a way to simplify that. 3 square roots of 5 plus 6 square roots of 5. Now what if I told you that this was just 3x plus 6x? Well, naturally you would combine like terms. You've got 3 of an object, and then you're adding 6 more of that same object into the mix, is going to give you 9 of that object. So over here, just tell yourself that object is the square root of 5. So we have 3 square roots of 5 plus 6 square roots of 5. That's going to be 9 square roots of 5. Cool beans. Again, they're just doing it slightly differently. What they're doing is they're taking 45 and they're dividing out the largest number they can that's a perfect square. In this case, they divided out 9 so that they could call it square root of 9 times square root of 5. Now, square root of 5 is nothing special, so you just leave it. The square root of 9 is 3. Now, 180 can be written as 36 times 5. We do that because 36 is a perfect square, and we can kind of branch it off that way. So this is one way to do it, but the way we were doing it using prime factorization is also very helpful, I think. And it's especially helpful because when you look at 180, you don't think of it as 36 times 5 right off the top of your head. So now, let's start simplifying the square root. Let's think about 18. 18 is 2 times 9, and then 9 can be written as 3 times 3. Why do we care about that? Well, we get the prime factorization because then I can write square root of 18. I take any pairs of factors I see, I bring them outside of the square root with a single representation. Now we still have the square root, and I got to leave what didn't get to come out inside of there. An alternate way is if you can make this connection right off the bat. If you can just tell yourself that square root of 18 is the square root of 9 times 2. Why would you do that? Because what you've done is you've taken the largest number that is a perfect square. 9 is a perfect square. And you've kind of branched it out of the 18. And then you can rewrite this as the square root of 9 times the square root of 2. Square root of 9 is 3. Square root of 2, I don't know. So we just leave it like that. The problem is this alternate way is a little bit harder if the numbers get larger. If the numbers get larger, it's not as intuitive in my opinion. So this becomes 3 square roots of 2. When you're in the text box, you can, let's just do it. when you're in the text box, you have all these options down here. So I put the 3 first, then I just picked the square root box. This could be used as a square root box. You notice it has 2 rooms for blanks. The upper room tells you what root you're taking. You can take the second root, which is the square root, or you can take the 3rd root, 4th root, 5th root. It just depends on what you have. This box is strictly square root, and it gets its own box because it's the most common kind of root usually. Let's try this one out. And this is good to just work some examples together, and I'm just working them straight up from your homework. Your homework will be similarly formatted to what you're seeing here, except the numbers might be different. But I don't mind working through stuff like this together. We have square root of 135. For the moment, let's ignore the square root and just think about 135 and do its prime factorization. Now the final digit here is a 5. If it's a 5 or a 0, that means the whole number is divisible by 5. So I know I can start by dividing it by 5. If you're not sure what the other number is, you're going to need to do 135 divided by 5. 5 won't go into 1, but it'll go into 13 twice. Leaving me 3, bring down the 5. 5 will go into 35 7 times. And it does so cleanly, meaning there won't be a remainder. And now 27 is not so bad. That's just, you can do 3 times 9. And then 9's not so bad. You can do 3 times 3. So now this is the only pair of numbers we see are the 3's. There happens to be an additional 3 out there. So now when we simplify square root of 135, well, we're going to take any pairs, we're going to bring them out to the front of the square root, but with just a single representation for that pair. It's like it gets cut in half almost. You still have a square root, and on the inside, you need to multiply what didn't get to come out. There was a single 3 here that didn't get to come out. There's a single 5 here that didn't get to come out. We're going to be multiplying them together inside the square root. Three square roots of 15. So 3 square root 15. Try this one on for size. Now, there's already a 3 out there. That's okay. We're just multiplying. We're going to take 75 and break it down. Well, 75, there's a couple things you might be able to see here. I know it as 5 times 15. You might also see it as 25 times 3, which is perfectly good because just think if you have 3 quarters, you have 3 25-cent pieces. 3 quarters is 75 cents. So same difference. So 25 is 5 times 5. 3 doesn't break down anymore. So the square root of 75 is equal to, well, here's a pair. It's going to come out with just a single representative from the pair. And you're still going to have a square root. And then you're going to have that leftover 3 inside. But wait, there's a twist on this one. On this one, we ignored the 3 for the moment and just did square root of 75. And we got 5 square roots of 3. But don't forget, there really was a 3 there. So all it's going to do is multiply to what we already found for the square root of 75. And now we'll do the 3 times 5 first. We'll get 15 square roots of 3. Bada bing, bada boom. We'll just go ahead and do this one. This one's interesting enough. We have square root of 7 times square root of 35. Now here's the thing. When you break down 35, it's just 5 times 7. And it doesn't break down anymore. So there's no pairs to take out. So here's the dilemma. We have to play a little bit of footsie with this one. There's nothing to break down in that way, but what we can do is rewrite this square root of 7. That was this square root of 7 that was already there. Now let's write square root of 35 as the square root of 7 times 5, which is exactly what it is. Let's break this up into 2 separate square roots. Like that. And ooh, look, I see a pair of square roots of 7s out there. We can bring them into the same square root house, and you'll see why we're going to do that. Because now when I take the square root and I've got a pair, they're just going to go down to a single instance of them without the square root. So we'll rewrite that. 7 times 7 is 49. And then square root of 49 is actually something. It's 7. So cutesy little trick there. We took the fact that 35 had a factor of 7, and this was a square root of 7 already. We basically were trying to get those 7s together. It's a little late Valentine's Day. We're Cupid trying to set these 7s up. So, you know, that's me trying to connect things to famous holidays that have ever happened. Let's see if there's a more interesting version of that. No. This guy, square root of 315 over square root of 7. Well, it'd probably help if we could simplify the square root of 315. Now 315 is, you can divide a 5 out of it. Five won't go into 3, it'll go into 31 6 times. Bring down the 5. And that's going to be clean, meaning that there won't be a remainder. So 315 is 5 and 63. And now 63, the only thing we can do with that is 7 times 9. If you remember your 12 by 12 multiplication table, you will remember that right away. And so now we can rewrite this as the square root of 315 is 5 times 7 times 9. There's no pairs. The only thing we're going to see is that these 7s could possibly do something. So we're going to take the square root of 7 out of it. The 5 and the 9 don't have anything special. So it's going to be 5 times 9. Now, oh, I just did something stupid. Because the 63, remember we did this. Yeah, let's just do it a different way. We could have branched off the 5 times 9, so we're just left with square root of 5 times 9. we could branch this off. I completely brain whiffed on that because the square root of 9 is 3. So this just becomes 3 square roots of 5 overall. So 3 square roots of 5. Square root of 2 plus square root of 98. How do I add those? You can't just add them and become the square root of 100. That would be great, but it doesn't work like that. Multiplication, you can bring them into the same house, but addition, you can't just do like that. So instead, we're going to look at 98. Now this one's actually tough to see what the heck 98 can be divided by. You might be at the drawing board for a little bit. Now we do see that we can divide 2 out of it. And then if you divide 2 into 98, you're going to end up with 49. $49 is then 7 times 7. Oh, look, that's a pair. So the square root of 98 can be written as 7 square roots of 2. So this becomes the square root of 2 plus square root of 98 is 7 square roots of 2. You take out a single representative. You still have a 2 left over inside. And then you have essentially 1 square roots of 2, because there's not a 1 written, it's implied, plus 7 square roots of 2, you end up with 8 square roots of 2. So they're trying to get you to simplify by making certain connections like that. We'll go ahead and do this one. 4 square roots of 18 plus 5 square roots of 32. They don't look like terms right now because the 18's on the inside of the square root, 32's on the inside. So it looks like there's nothing we can do about that. But actually, we're going to have a pair of numbers. So square root of 18 can be written as 3 square roots of 2. And then don't forget, there was already a 4 in front of it. So 4 square roots of 18 can be written as 4 times 3 square roots of 2. Now 32, well, there's a couple ways you can write that. You can call that 4 times 8. 8 can be written as 4 times 2. The 2's. And so you have a number of pairs. You have a pair here and a pair here, but then you have an odd man out 2. So square root of 32 can be written as a single representative of this pair, another representative, so another 2 gets multiplied in. We still have a square root, and we have this 2 inside of it. And then we also had that 5 in front of it that gets multiplied in. And so what we end up with, 4 times 3 is 12. We have 12 square roots of 2 plus 5 times 2 is 10, times 2 again is 20. And then there's still the square root of 2 there, so we have 20 square roots of 2. And now you have 12 of an object plus 20 of that object. You're going to end up 12 plus 20 is 32. You're going to end up with 32 of that object, 32 square roots of 2. Last one, square root of 24 times the square root of 6. Let's break each of these down. So here we have a pair. Here they don't have any kind of pair. So square root of 24 can be written as, bring out a single representative of that pair, 2. What we have left over is the square root of 2 times 3, which 2 times 3 is just 6. So we have 2 square roots of 6 on top. On bottom, if you look at 6, 6 doesn't have any pairs that can be broken down or taken out. So you just have that square root of 6 on bottom, and the square roots of 6's cancel, leaving you with just 2. So a pretty cool little thing overall.